Good morning, good evening. Welcome everyone, wherever you are today. This is Dr. Stephanie Smith. Very happy to be with you to tell you about how to get your lab ready for HABs. We are using the GoToWebinar interface today. This may be a reminder for some of you, if you're not as familiar with this, since we all use Zoom or Teams, this is a popular platform still for doing webinars. And part of it is because we can engage with you a little bit better. So make sure you can hear us loud and clear. If you're having any trouble, use that chat feature to let us know. I'm joined by a colleague today that can help you if you're having any issues, and he'll be keeping an eye on that chat. That's Michael Watt. If you're connected to a VPN, I would advise you disconnect it so that you'll get better video quality. But boy, what I really hope is that you're going to ask us a lot of questions using that question feature. And then, of course, I'll pause in between sections to see if we have some other questions. Please engage with us. Let us know what you have questions about, and we will go from there. And I noticed that somebody asked if they could admit other participants or whether the deadline was over. That's a good question, and I'm not sure. So I'm going to let Michael try to type an answer for you to that chat. So moving forward, I am Stephanie Smith. I've been doing this for a while now, and if you want to know how long I've been doing this at YSI, I actually have my own webpage at ysi.com. This is a hyperlink to it. You can find me on Twitter, where my handle is @waterwoman, and I'm also on LinkedIn. I'd love to connect with any of you, so please join me there on our social media. We also, if you're interested in the topic of harmful algal blooms, we have what we call the HAB Hub. It is a web page dedicated to all the things that I and some of my other colleagues have been doing related to harmful algal blooms. These are videos and webinars that I've done over the years, and some of you may have joined me for some of those in the past, and we have this web page as well. I grew up here in Missouri, which is where I'm coming to you from today. That's where I started my education, which I completed at the Ohio State University, where I got my degree in microbiology. So I really originally came to this topic as a microbiologist. I want to acknowledge my colleagues Tim Smith and Cynthia Elmore. They are really the brains behind a lot of what I'm going to show you today. They are the ones who have developed these methods, perfected these methods, and they're also the ones who would probably be better at answering your questions were it not 6 o'clock in the morning here. So if I have any trouble with your questions, I will keep track of them and get back to you. So let's get to it. We're going to talk about harmful algal bloom monitoring and why you need methods like this in the laboratory, even though most stuff I've talked to you about in the past has been about doing monitoring elsewhere in the field, really. So first of all, let's talk about the root cause. We already know that freshwaters around the world are carrying nutrients from a number of different sources, whether it's agricultural runoff, fertilizer runoff, human and animal waste, and those streams, rivers are carrying those things straight to our coastlines. We have good estimates that in the United States, for example, 78% of our U.S. coastlines are affected now by this nutrient runoff, which we collectively call eutrophication. In Europe, they know that 65% of their coastlines are estimated. We're pretty confident, as I'm sure you are, that that's a problem globally, but we really don't have complete enough data to say what those percentages are. But we do know that harmful algal blooms in both our freshwaters as well as in our brackish and even oceans now are experiencing various types of harmful algal blooms. And of course, those have a lot of impacts on the environment. One of the most common and insidious is reduced dissolved oxygen, known as hypoxia or anoxia. This is where we get things like dead zones. And of course, toxins affect wildlife. We know that there have been a lot of mortalities, for example, of dolphins in Florida here in the US, of manatees. And here in the US, we are big pet lovers, and dogs often now are killed by harmful algal blooms because when they're swimming, they gulp in a lot of that water, and those toxins are very, very tough on their livers. So the drinking water impacts, though, are just as insidious. Of course, those toxins can affect us, and that has become a problem now globally, that we have to be very cognizant of removing those toxins from our drinking water. But one of the things that almost everyone has experienced in some form or fashion is taste and odor issues with their water. That is due to 2-methyl-isoborneol, which is going to be called MIB, and geosmin, which you'll hear me talk about a lot today, particularly in the third part of our session. But of course, these things have economic impacts as well. Over $1 billion has been estimated just here in the United States for remediation issues related to harmful algal blooms. And this increases the costs of water treatment as well, having to clean clarifiers and add things like advanced oxidation and so forth to handle both those taste and odor and toxin issues. And a big issue now is we have to use our lakes and streams and coastlines differently to avoid the effects of harmful algal blooms. I was in Florida during a red tide, and we all had to wear face masks to avoid inhaling those brevetoxins. That's something we used to not have to do. And so it really does affect how we use our waterways. I just noticed my camera is not on, so I apologize for that. I typically like to show myself when I'm presenting, so I feel like I'm engaging a little bit more with you. All right, there it is. Whoops, that's not where we want it to be. There we go. I hope I didn't screw up sharing my screen. Michael, will you just give me a little clue whether you can still see my screen there?
Screen looks fine, Stephanie. You're good.
Okay, thank you. Thank you so much. All right, so let's carry on then. So, of course, there's a big relationship between water quality and harmful algal blooms, and that includes the way water quality drives harmful algal blooms and responds to harmful algal blooms. And those drivers that we were just talking about, of course, are nutrients, especially phosphorus and nitrogen. Increased temperatures and decreased flow also, particularly in freshwater systems, enhance harmful algal blooms. But that water is affected. I already mentioned decreased dissolved oxygen. And an interesting note, when we talk about fish kills, for example, that are related to harmful algal blooms, it is typically because of the decreased oxygen. It's not because of toxins. But the act of photosynthesis that these algae are doing increases the pH, which is also very damaging to a lot of aquatic life. But the increase in pigments, just due to the increase of biomass in the water, that has a few different effects, but it is also a tool that we can use to understand the growth of algae in the water. And that really is the basis for how we do field monitoring for harmful algae in the water. Is we use sondes. Some of you are already going to be familiar with the ExoSonde platform. Sondes are really your best tool for monitoring for harmful algal blooms in a water body. They'll give you continuous data acquisition if you have this connected to a telemetry system. And they are excellent for giving you very good measurements of dissolved oxygen, temperature, and pH. All of these are responding or driving harmful algal blooms, as we just mentioned. Now, when it comes to chlorophyll and phycocyanin, which are the primary pigments in blue-green algae, you can measure those with a sonde. It is what I would call a trending measurement, not really an absolute measurement. And the same is true for if you're measuring in a saltwater environment, phycoerythrin, but then some of these other critical parameters like nitrate, one of those nutrients that causes eutrophication, turbidity, and dissolved organic matter. These are all what I would call trending measurements that you can acquire with your sonde. You can create correlations of those measurements in the laboratory. So sondes can't give you some of these other things, though, that you would be interested in for a harmful algal bloom monitoring program. They can't tell you specific species of algae, such as you can get with a flow cam or a microscope. They can't measure toxins for you, though in some situations those pigments are an indicator of the toxins. They can't measure phosphorus or orthophosphate, and they can't give you high precision measurements of these other parameters that are definitely of interest when you're doing harmful algal bloom monitoring. And so if you want to have a very robust harmful algal bloom monitoring program, you really have to balance field measurements with measurements in the lab. And in reality, most measurements still are done in the lab. People are using ELISA or LC mass spec for measuring toxins, and the good old-fashioned tried and true filter it, extract it with a solvent, that is still the way that people do chlorophyll extractions, chlorophyll measurements most often. And of course, algae speciation has to be done with a scope. Today, I'm going to talk to you about these other highly relevant measurements related to harmful algal blooms. While we're on this slide, I want to bring your attention to this little green button here. You're going to see green buttons like this throughout the presentation, and you'll get a copy of these slides. Those are hyperlinked to various resources that you can get online. In this case, I wrote a blog earlier in the year about the importance of sample collection for water quality monitoring. So keep your eyes open for those little buttons. They'll take you to some resources you can follow up with. One of those is the brochure for what is called our FS 3700 Automated Chemistry Analyzer Platform. You'll hear me call this the ACA in some cases. That is one of the platforms we're going to talk about today. It is a high throughput platform that you're going to be able to use for measuring phosphorus and nitrates and total Kjeldahl nitrogen, as we'll discuss. We did just add an auto diluter to this platform, which just makes this a really wonderful, pretty much hands-free way to get highly accurate measurements of these nutrients that we're talking about today. And it also comes with what we call cartridges that go in here. They are pre-configured to make it very easy for you to do these measurements. So you don't have to make up all the reagents that are required to do these assays. This really does automate the process. The other system we'll talk about today is where we have added our 4100 auto sampler and our 4760 purge and trap to an Agilent GCMS system for measuring Goesmin and MIB. So to summarize this first part of the talk, if you want to manage harmful algal blooms, you've got to be measuring the right stuff. And that means having a strategy both in the field and in the lab. And when it comes to understanding the drivers of harmful algal blooms, the most important thing to understand are those nutrient inputs. But drinking water managers, the thing that really makes the phone ring off the hook is taste and odor issues, Goesmin and MIB. And so nutrients and taste and odor compounds both are best measured in the lab, and that's what we want to talk about today to equip you for that. So I don't see any questions right now. I do want to encourage you, if you have any questions, to type them into that question panel. And then Michael is also watching the chat for you if you need any help. So I will be focusing a lot today on EPA methods. And, that's not just because I'm in the US, it's also because globally, a lot of people start with these methods, and these are methods that get adapted in a lot of different regions. There will be some exceptions to that, particularly when we talk about Goesmin and MIB. But we're going to talk today about measuring what's called total Kjeldahl nitrogen, or TKN, as you'll see it in the slides. We're talking about this in accordance with EPA Method 351.2. One of the reasons we're talking about TKN is because the EPA actually doesn't have what's just called a total nitrogen method. And that's because their definition of total nitrogen, actually everyone's definition of total nitrogen, is total Kjeldahl nitrogen plus nitrite plus nitrate. So what is TKN then? It is organic nitrogen plus ammonia plus ammonium. And so when we look at the sources of nitrogen that can get into a water system, of course, there are point source and then non-point source sources of that that all can get into the water. And so TKN really is telling you more about animal originating runoff. And by the way, that includes humans. So in a water body, you can get nitrogen through a number of these sources and in a number of chemical forms, but total Kjeldahl nitrogen is really helping us understand the sources that originate from animals. So it's a good indicator of runoff, wastewater runoff. For harmful algal blooms, I will remind folks that algae can sometimes fix atmospheric nitrogen, or sometimes they're using nitrogen that's already in the water in the form of ammonia, nitrate, nitrite. TKN then is representative of those highly assimilable forms. So for the algae that cannot fix nitrogen, which, by the way, if you look at microcystis, for example, one of the most insidious toxic algae, it doesn't fix nitrogen. And so TKN is really relevant when you're talking about harmful algal blooms. The other thing we have seen in the literature is that ammonium in the water can increase toxicity. One might speculate from a biochemistry perspective that that's because many of these toxins, which are basically peptides, which are like proteins, ammonium stimulates protein production too. And so ammonium and urea may lead to increased biomass for microcystis and toxin production. And there is some literature here for you to look at to help you understand that. So when we talk about measuring total Kjeldahl nitrogen, let's jump into what the method is that we are using, method 351.2, and how we've adapted it for the FS 3700. So first of all, you start by doing a sulfuric acid digestion of your sample. So this TKN digestion is a very common step. You don't actually do the digestion on the FS 3700. You can do that manually, or there actually are instruments we have that can automate that for you if you want to do high throughput digestion. So You also add potassium sulfate in those reactions. That raises the boiling point to 380 degrees Celsius. And then there's a copper catalyst that's also used. That is going to help you convert all the available organic nitrogen into ammonium. So remember, with TKN, we're trying to get that total organic nitrogen measurement. This is definitely the longest step of the entire process, is doing this digestion, and it can take about 2 hours. Now, that ammonium sulfate, that complex nitrogen that you just made, is going to be in a solution, and we're going to add sodium hydroxide to raise the pH to over 11. That converts that ammonium sulfate into ammonia gas. Now, the gas diffuses through a hydrophobic polypropylene membrane during the digestion, and it reacts with a sodium hypochlorite solution. And that reaction between the ammonia gas and the sodium hypochlorite yields chloramine. So this is described in the method abstract that you can find online. The next step, this is where we do what's called the Berthelot reaction. So the chloramine is going to react with salicylate to give indophenol blue. Those chemists out there know that this is a very, very common color indicator in a lot of chemistry reactions that we do to detect nitrogen compounds and other stuff. So the indophenol blue that you generate, if we trace back through these steps, it is proportional to the ammonia concentration and to the total nitrogen concentration that was in that original sample. But sometimes there's not quite enough of it to see. And so we complex it, we add sodium nitroferrocyanide to intensify that blue color, which we then can detect at 660 nanometers. Now, this reaction is pretty convenient to do in the lab. Most ammonia methods use a phenolate, and the most popular TKN methods use the salicylate, which is pretty cheap, pretty easy to get, and this is pretty easy to perform in the lab. All right, so that sounded like a lot of chemistry, and we actually do try to make that easier for you. Again, you can automate that. Doing particularly that Berthelot reaction, we have optimized that for you with the cartridges, what we call the cartridges that come with the FS3700. If you want to know the exact part number for doing that, I've provided it to you here, and it gives you all of the chemistry that you need to get this done. The only thing you'll have to come up with is that sulfuric acid to do that digestion on the front end. So we've optimized this for the 3700. And by the way, this cartridge can actually be used for some other EPA methods, and you can read about that when you get that method abstract. We also offer a single cartridge for nitrate and nitrite, because remember, if you want to get total nitrogen, you'll have to measure these as well. So today I'm just focusing on TKN because it's highly relevant for your algae monitoring. But if your regulatory environment requires you to actually back out and get total nitrogen, the FS3700 has one of our most popular cartridges for measuring nitrate and nitrite, and you can measure those to get to additively get total nitrogen. But this method that I'm talking about, for those of you familiar, this is called a segmented flow analysis method that we perform on the ACA. And you can also use the same cartridge as I was just mentioning to measure, do EPA method 350.1 then you'll have to buy another cartridge to do nitrate and nitrite if you feel like you need to measure those to get your additive measurement of total nitrogen. Oh, here is an example generated by what's called FlowView software on our ACA platform. So this is from a wastewater treatment plant in Liverpool, Ohio. They are measuring TKN in their influent, in their effluent, their outfalls, to protect all the surrounding bodies of water from nutrient runoff. So on the left, this is basically the peaks that are generated for their samples. So they had a number of different samples, but prior to doing that, they ran this calibration curve that you can see here, and the measurements of the concentration that is calculated for these peaks is derived from that calibration curve. So a nice thing about FlowView is it allows you to verify the proper integration of these peaks, and it does all the calculations for you using that calibration curve. So when you're looking at the calibration curve and you want to know the quality of it, if you will, one of the things you look at is the relative standard error. Notice in this case, it is almost 50%, which might surprise you when you look at this curve. It looks pretty tight. But this is pointing out what you often see with manually performed dilutions. So they manually perform their dilutions for this method. I want to show you by comparison, if you do the same thing using the auto diluter that I had mentioned previously, now you're dealing with more like a 6.5% relative standard error. So this gives you an example of how that auto diluter really helps you get very good results. And we see this really across all of our methods. When we use the auto diluter, we generally see far less variability from one calibration to the next. But what does this mean in terms of how well this method actually performs? We do have a way that we assess that. So we look at the range, and in this case, you can get 0.01 to 20 parts per million nitrogen, total nitrogen measured, total Kjeldahl nitrogen, I should say, measured with this method. And if you use the complete setup with the auto sampler, you can crank through over 40 samples in an hour. So that's a pretty great throughput rate if you're collecting a lot of samples and want to push those through your lab. The precision is fantastic with this method at less than 2% of a relative standard deviation at the mid-range of the calibration curve that we described for you in that method. And the method detection limit is fantastic, really at 1.2 ppb, which is generally far lower than you're really going to need when you're measuring TKN in a eutrophic environment. So the range on this can be adjusted, by the way, by increasing or decreasing the load time in your segmented flow and method. You can also change the loops. Some of you that are familiar with the ACA will know what I'm talking about there. You can change the loop if you're running this as a FIA method, a flow injection analysis method. Also, the sample rate can be increased. So you're cranking through here by reducing the cycle duration in any of the methods that we make available to you. So this aligns very nicely with the EPA's requirements for this method, but there are some things for you to be aware of that Tim wanted me to warn you about, because he has done this hundreds of times. And he says that the TKN method, it does use a hydrophobic membrane, and so you really have to be cognizant of how that might interfere potentially with things in your sample. You need to filter turbid samples. If you're getting samples directly out of the environment or from certain steps in your wastewater treatment process, you might need to filter them. He recommends filtering with a 40 micron membrane, a Wattman membrane. The other thing is that heavy metals in the sample and in digest can interfere by precipitating out. You can remove those by using citrate, sodium citrate, to complex them. But then again, if you're in a wastewater treatment plant, you need to be cognizant of the potential impact of residual chlorine. You can, of course, remove that using some sodium thiosulfate before analyses. So that brings us to the close of our TKN part of the presentation. Just to remind you, the reason we're measuring TKN is because it's very important to understand eutrophication that stimulates harmful algal blooms. And you cannot measure TKN with an instrument in the field like a sonde. You have to measure it with a colorimetric method. The FS3700 platform that I was just describing to you has pre-configured chemistry cartridges, auto dilution, and methods that we make available to you to automate the process. And if you pair it with the nitrate and nitrite methods, which you can actually run on a second channel right on the same platform, you can derive total nitrogen. So I'm going to pause there, and I don't see any questions right now. I don't know, Michael, if there's anything you see that we need to follow up on in the chat, or should we just go ahead and scoot right on?
Stephanie, I don't see anything either. I think everything's running around smoothly. It just reflects how clear your presentation is. But if I could take this opportunity to just let all of our attendees know that we will be preparing an email blast for all registrants, which you will receive in a couple of days, which will include Stephanie's presentation, as well as a link to this recording so that you can view on demand.
Excellent. And that we really appreciate Michael and the team making that available to everyone in the region. So I will carry on then. You know, when we talked about eutrophication, we talked about nutrients, and phosphorus is one that probably gets twice as much attention when we talk about harmful algal blooms. Total phosphorus is all forms of phosphorus that you get in the environment, and there are multiple inorganic and organic types of phosphorus coming from a lot of those same sources that we talked about before. Now, one of the reasons that phosphorus gets so much attention is because when it comes to algae like microcystis, in freshwater systems, phosphorus typically is the limiting nutrient. And so when you get enough of it in the water in those eutrophic and hypereutrophic conditions, that's when we really start to see these massive algae blooms in freshwater systems. A very interesting thing, some of you may be familiar with something that is called the Redfield ratio, the nitrogen to phosphorus ratio. That actually is sometimes a pretty reliable indicator of your harmful algal bloom risk in a system. So when you pair something like the TKN method that we just talked about with method 365.4 for total phosphorus, that can be a very good indicator for you of whether or not you might be at risk for a harmful algal bloom. So let's look at the segmented flow analysis that we've developed for measuring phosphorus. Again, the green button on this slide will take you directly to our abstract for this method, but it begins exactly the same way that the TKN method began, where you're doing a sulfuric acid digestion. So prior to analysis, you do this via the same Kjeldahl digestion, and what you're doing here is you're hydrolyzing phosphorus to generate orthophosphate in the form of phosphoric acid. So this is basically just like the TKN digestion we discussed earlier, and some of the other instruments we have that you can use to automate that are also available for phosphorus. Now, the analysis is going to be accomplished by reacting with an ammonium molybdate antimony potassium tartrate solution, which is a bit of a mouthful. But what you're really forming here is phosphomolybidic acid. This is going to become the primary reactant going forward. So the antimony molybdate complex is called molybdenum blue, and the intensity of this is going to be proportional to the amount of phosphorus that was in that original water sample. Now, if you only have to measure orthophosphate, the digestion step can actually be omitted, and you can do this process actually directly. But if you want total phosphorus, you have to do that digestion to convert everything to orthophosphate first, and then all of that will end up being in this complex. So we have focused in this presentation on the 365.4 method, but there are actually several other methods you can use for measuring phosphorus depending on the concentrations and forms that you might expect. And I've provided these links for you if you want to look at those. But and some of you may be using standard methods or ISO methods, for example. You may want to be, there's a popular UV persulfate method that some people prefer, and all of those are available to you on the FS3700 platform. But why don't we continue to move forward, and I'll show you another real world example of us using the 365.4 method for measuring total phosphorus. So we're back to our Liverpool, Ohio wastewater treatment plant here. And they are measuring TKN, as I showed you previously, and they are also measuring total phosphorus. So they are using both of these methods together to understand their impact in potentially stimulating harmful algal blooms. So this is also really important for them because they have discharge limits for total phosphorus. So if you're familiar with the NPDES permitting, the National Pollution Discharge Elimination System here in the United States, this method is what they use to stay in compliance with their discharge permit. So again, in this sample, they were using manual dilution, and you may notice that they did a lot better on this method, and that is actually a sign of how robust this method is. So in this case, they got a relative standard error of around 10%. We can tell you from experience that if you do this with the auto diluter, you can easily cut that relative standard error in half. But they've done the same thing here. They've generated their calibration curve, and they've run their samples, and they've done full peak integration of those samples to get the concentrations of total phosphorus in those samples. So some things that they had to consider for those samples are very similar to what we talked about for TKN. If you have a very turbid sample, you definitely are going to want to filter that. And you also, in this method, as well as the TKN, need to be cognizant of color that might interfere with those measurements that you're doing at 660 nanometers. Now, something that is really, really important, and we want to emphasize this, is that phosphate is a very common contaminant of laboratory glassware. And that's because we typically use a detergent when we wash glassware in the laboratory. That residual phosphate can really interfere with this assay. And so you need to make sure that you have acid washed all of the glassware that's used in this example, or in this method. And we recommend using I recommend using at least one normal hydrochloric acid. Back in the day, we used to use nitric acid for this, but I think people don't want to dump that into their plumbing as much as we used to. And there are other compatible procedures for removing or suppressing interferences. So this is a more contamination sensitive method. I think that is all I wanted to mention on that. The method performance is really, really robust. So again, we have a really excellent range on this. And the throughput is actually higher even on this method, with an excellent precision again and an excellent method detection limit. Now I noticed, let's see, we have a couple of questions here. So before let me wrap this up and get some of these questions, but let me summarize what we just talked about in this section. So total phosphorus, as I mentioned, is a very relevant parameter for measuring, for monitoring for harmful algal blooms. And you really do have to take this one into the lab to get highly accurate measurements. As with total Kjeldahl nitrogen, nitrate, nitrite, this platform will really automate that chemistry for you, which is going to just make your life so much easier. So I want to answer a couple of questions. I want to thank Tufam for his question, or her question, my apologies. And it is, what is the importance of the N to P ratio for growth of the algae bloom? So to remind everyone what that question is about, I mentioned on this slide right here, the N to P ratio. This is sometimes called the Redfield ratio, and it's really, really important particularly in saltwater environments, but they have come to learn that it's very important in freshwater environments as well. So phosphorus, as I mentioned, is the limiting nutrient for algae in most freshwaters. And so for many, many years, we just focused on phosphorus. But Hans Perl and a lot of the other leading scientists in this area of study have noted that nitrogen matters as well. And so what we've learned is that the higher that ratio, the greater your risk of having a harmful algal bloom. And so it's not just a matter of looking at phosphorus. You really have to understand both of these nutrients for really understanding your risk. And that ratio is different in different systems. So my recommendation is that you measure nitrogen, total Kjeldahl nitrogen, you measure total phosphorus, and you do it with a lot of different samples. And at the same time that you're doing that, you're also looking at total chlorophyll and your abundance of algae in those systems. And you're going to start building that relationship for your specific system that you are looking at. So there isn't a one size fits all answer to your question, but there definitely is a relationship and a correlation that you can likely build for your system. So I really appreciate that question, because that is a way that you can use the tools we're giving you to get a different level of information when you're doing harmful algal bloom monitoring. Philemon has asked, whether we have any remote sensing meters for the different parameters. That's a great question, Philemon. So the EXO nitroled sensor can be used for measuring, I should say monitoring trends in nitrate and nitrite directly in the water. So that EXO nitroled sensor is definitely a game changer. Phosphorus, you can't really look at that way, because the one exception is the IQ SensorNet system is a very popular system that Xylem produces for measuring a lot of different things actually in water. It is still a wet chemistry system, and it does come equipped with a full telemetry system that can be fully integrated into your SCADA in a wastewater treatment plant. So that is a phenomenal system. When people use it for measuring the same things we're talking about here, you still have to back those measurements up in the laboratory. So it is a monitoring system. It does very, very good measurements, but people still collect samples and verify or validate those samples in the laboratory very often when they're using that system. Someone asked about the wavelength for the phosphorus complex. I have to apologize. I think it's 660 nanometers, because it is it is that molybdenum blue. But if you go to the green buttons on those methods that I was talking about earlier, it will have that wavelength for you. I'm pretty sure it's 660, but double check that by going to the hyperlink for this method. And then someone is working with biofouling on an RO membrane in a desal plant. And they're wondering if there is a way to monitor the biofouling caused by algae, and whether that should be based on the chlorophyll content or the N to P ratio. Wow, that's an excellent question. And I've done something similar to that. And what I have done is I've done chlorophyll extractions to get sort of, you're trying to understand the relative ratio of algae in that biofouling to everything else that's in the biofouling. So I would recommend doing that with a chlorophyll extraction. You had asked whether an N to P ratio would be the way to do that. That is not what I would recommend for looking at the biofouling on a membrane, because the N to P ratio isn't really telling you what the biomass is that is there. N to P is more of a water quality measurement to tell you what your risk is of developing a harmful algal bloom. But if you want to look at biofouling on an RO membrane, I would scrape a sample off of that membrane and I would do a chlorophyll extraction on it. So that's a really great question, and thank you for asking that. Really wonderful questions, guys. Thank you so much. And let's get on to the last part of our presentation, which is to talk about the taste and odor compounds Goesmin and MIB. So, if you've ever walked outside after a rain and you kind of smell that earthy smell from the soil, that is from Goesmin and MIB. A problem with that in water, though, is humans really hate the taste of it, and we can detect it as low as 5 parts per trillion. That T is trillion, not thousand. So it is made by microorganisms, for my microbiology friends out there, the streptomycetes, the actinomycetes, but these are volatile, non-toxic compounds. These would have to be at ridiculously high concentrations to be a health risk. But they are made also by some blue-green algae, which I remind you all are actually bacteria. But they're not made by all of them, and they are not made all the time, but they are often an early warning sign of a harmful algal bloom. And so you can detect these compounds at very, very low concentrations, and it sometimes can be a sign to you that a harmful algal bloom is starting to occur in your drinking water reservoir or in of receiving water that's getting effluents. Now, in one study, Goesmin and MIB were found to be very good indicators of toxin production in the water. And so we can't say that that would be the case all the time, but this is another example of where you pair your methodologies to see what correlations might exist in your system. And then I also want to point you to a really cool technology we have that can help you remove these compounds as well as toxins that might be caused by harmful algal blooms. So if you're folks on the drinking water side of this conversation might be interested in checking out that technology. Now, because humans can detect this at so low concentrations, we try to come up with a method that can detect less than 1 part per trillion in finished water. Excuse me, I'm going to take a drink of my tea here. Thank you. So we do this using GC mass spec with selective ion monitoring. Using SIM is absolutely necessary to get this level of sensitivity and specificity at the same time. It also means that you're probably going to have to pre-concentrate your sample. So the most common way that people do that is through using something called headspace solid phase microextraction. That means that a fiber isn't submerged into the sample, but just into the headspace. Hang on just a minute, guys. I need to call. Ooh, forgive me. My throat's getting a little dry there. So the fiber that is this fiber that is put into the sample, it is a fused silica fiber that has a polymer coating, and the analyte, when you purge the sample with a gas flow, it volatilizes and it adheres to that fiber. And then you take it out and basically you heat it to desorb what has adhered to that fiber. So variability in this process, I mean, you have to get good adsorption and then very consistent desorption before that sample goes into your GC loop. There's a lot of variability in that. And that's one of the reasons that we thought we wanted to try this with our purge and trap system. And in a purge and trap system, it's a little bit different. It's a little more direct. You're not counting on that absorption, desorption in the same way. So what you do is the purge gas goes through the sample as very fine bubbles, and it pushes that the Goesmin and MIB through the excuse me, it pushes the sample onto the trap, on the purge and trap. If some of you are already familiar with our purge and trap system, you might know that the most common trap we use is the number 10 trap. If you're using our Eclipse purge and trap, we actually use the number 7 trap in this method. In any case, instead of adsorbing onto that fiber, you're collecting those analytes in this trap, and then they are going to be purged out and flowed into the detector on the system. Now, one of the things that we like about this approach is that the extraction, the concentration, all of that happens in one step. So there's a lot less handling of the sample, and there are fewer places for things to go wrong. And so generally speaking, we see less variability with this method than we see with SPME. Now, as a reminder, we're doing this with OI Analytical's 4100 autosampler, which is equipped with an LV20 manifold that helps us collect those volatiles, send them to the Eclipse purge and trap, And again, we've equipped this with our number 7 trap, and then we have it hooked up to a 7890 GC 5975 mass spec system. This does work, by the way, with the 8890 if any of you are using the newer Agilent system. Okay, so what were our goals in doing this? Because as I've already mentioned, the SPM method is very, very popular. People have been using it for a long time. However, we wanted to obtain very high sensitivity. I mentioned to you that at least a part per trillion was our goal. You can get that with SPME, but we wanted better reproducibility. And we also wanted to use a method that labs are already familiar with. And that's one of the reasons we're using EPA Method 524.3. A lot of labs are already set up to do this for monitoring for volatile organic compounds in waters. And so by optimizing it on that same VOC method, you can kind of readily switch over to doing your Goesmin MIB monitoring during algae season by basically just changing from your number 10 trap to your number 7 trap on this platform. Now, another thing we wanted to accomplish is in the past, people have used purge and trap systems for looking at Goesmin and MIB, but you have to add salt as a pre-treatment step to your samples. We wanted to see if with this newer purge and trap, we could get the same or better results without salting the samples. The other thing we wanted to accomplish was using less sample volume. So again, because it's such a sensitive need here to get that less than 1 part per trillion, people usually achieve that by using really high sample volumes. We wanted to see if we could cut that sample volume in half. And that was really important because this method actually prescribes using a 5 mil sample volume. So this is one of the ways in which we are actually slightly deviating from the method to achieve the results desired. And then we also wanted to lower the temperature purge because that's frankly less stress on the purge and trap system, and you get more life out of it if you can use lower temperatures. So how did it perform? So in this method, I don't have it shown here, but we use 1,4-dichlorobenzene D4 as an internal standard. And then what I've shown here is the surrogate standard, which is 1,2-dichlorobenzene D4. The D4 is the deuteration for my mass spec folks. That's what the D4 refers to. We use those standards at 10 parts per trillion. Now, something about this method that is unique is that it makes you recalculate every single point of your calibration curve to meet a % recovery criteria. So on the lowest point, which in our case was 1 part per trillion, you have to have plus or minus 50% recovery. On the high end, which in our case was 100, you have to have at least 30%. And so you can see that we very, very easily met those recovery criteria for this method. And then also, really nailed the standard concentrations. And so reminding you again that this one was at 10 parts per trillion, but these are Goesmin and MIB at 1 and Goesmin and MIB at 100. So really the method performed quite beautifully on using the Eclipse purge and trap. Now, of course, sensitivity is one of our most important criteria when we're trying to get that 1 part per trillion target. That is defined as what's called the minimum reporting level in this method. You do the same thing of evaluating 7 replicates, And in this method, they use something called the half-range prediction of interval results, the PIR. And we are hitting the PIRs that are required for this method. And I'm noticing I'm running up against time. So I'm going to just go through these last initial demonstration of capability where we are also hitting all of the targets that are prescribed by this method. So to wrap this one up, the one thing I want to point out here is that when you're trying to get the level of sensitivity that we got with this method, you're going to want to have a lot of replicates, and you're going to want to use pretty clean water. We have not done this with source waters. We've done this with finished drinking water. We are getting ready to trial this method with water from an aquaculture system, actually. And we'll look forward to providing those results for you. So these are insidious compounds in drinking water, and you want these detection limits. Actually, in some parts of Asia, where much of today's audience is, you actually are regulated for the concentrations of Goesmin and MIB in your drinking water. So we hope this method will be very, very helpful to folks that have to meet those regulatory limits and you can adapt this easily to the methods that are required in your region. And so with that, I want to thank you guys very, very much for your attention today. One of the things we do want to make sure of, let's see, Michael, I'm trying to launch a poll for you. And it is not launching.
I'll launch it for you, Stephanie. Just a moment.
Okay, thank you. So I don't see any further questions. Philemon has asked us to forward the brochure on remote sensing probes and meters. So Philemon will send you stuff for both the EXO platform as well as the IQ SensorNet platform. So Michael and Rumiko will follow up with you on that. Let us know with this poll that Michael has launched for you whether or not you want us to follow up with you. We'll be more than happy to do that. And someone has always also asked if we could they could do a presentation on our products. Nothing would make us happier, Philemon. So definitely reach out to your team there, and we'll figure out how to do that. I have nothing further, Michael, and I don't see any more questions.
That's terrific. That just, again, shows how informative your presentation was. Thank you so much, Stephanie, for your time, especially at 6 a.m. in the morning. We truly appreciate your contribution to this topic, and I hope the audience also appreciated the presentation. Just a reminder once again that we will be sending out a follow-up email in the next couple of days, which will include a link to this recording as well as a link to Dr. Stephanie's presentation.
Thank you so much, Michael, and I really appreciate the audience. It's always my pleasure to join my friends on the other side of the planet. So everybody have a wonderful evening where you are.
Thank you, everybody. Thank you, Dr. Stephanie. Have a great day.